This is a crash course in some of the archives that we have here at IPAC. But before we talk about the specific archives we have here at IPAC, let's go over a little bit of context. Why do we even need to have archives? You actually already have a sense of why we might need to have archives, because if you've ever tried to find a photo in your own archives, you already know how hard this is. You probably have a cell phone, a smartphone, on which you've taken photos. Probably you can remember a particular photo from a particular event. Like, gosh, I really want to find a picture of my kid on that day when he did that particular thing, or my partner when he did that particular thing, or I really wanted to find that selfie that I really liked. Well, unless you remember what specific date it was, it might be hard to find it. And when you get a new phone, it's going to take a long time to transfer over all of those photos. And if you have a separate camera, managing all of those photos can be challenging. Do you put them on the laptop? Do you keep them independent? When you have a big family event of some sort, you probably have photos from your phone and your partner's phone. Do you combine them? Do you share them? It quickly can get out of control. It's certainly true that a lot of these companies are trying to develop tools to help you easily find a photo in your own archives, but it's hard. It's hard to do it quickly and efficiently. That's why we need archives, astronomical archives, because we need to be able to find data quickly and easily. For decades, if not centuries, when you were taking astronomical data, you just took your data home with you when you left the telescope. So, you went to the telescope, you exposed your photographic plates, and when you left the telescope, you took those plates with you. A corollary to that was if you didn't have access to a telescope, you didn't get any data. That was just the way that it worked. Very early on, there were archives where you could go and just download your own data. And when I say that, I mean unreduced data. I mean data that aren't ready to use right now. They're data that need some processing before you can use it. Maybe from these early archives, you might look for other data from a particular location on the sky or from a particular data set that you knew was there. But you didn't go to the archive to see what was available. You already knew that the data were there. And really the philosophy was, I'm just going to download all the data and I'll figure it out later. But now we have to support that kind of use, but also because almost all of these telescopes are from publicly funded assets, meaning that they're taxpayer funded, we have a mandate to make those data accessible to the public. And a corollary to that is if your institution or your country doesn't have a telescope, you can still get data. And that is a far more equitable approach. So when you go to these archives, now you can go with a mindset of, are there other data on my target from another date, from another survey, from another wavelength, from another telescope, and go and see what's out there. And you can also go and find some data that are ready to use right now that somebody else already did all the hard work on that I can just pick up and use today. I can also look to see if there's other similar data on similar objects that I didn't even know were there when I started. Soon, because the data are getting bigger and bigger and bigger, we're going to be in a situation where we literally cannot pull all the data out of the archive and take it home. So there's going to have to be some analysis that happens at the archive before astronomers take it home. And this is a huge sea change in the way astronomers think. Not all astronomers are taken to this easily, mind you, but it is happening. So the mission of an archive is evolving right now from a search and retrieve mentality to do some analysis at the archive and then just take some of it home to work with. So an archive's job is to both ingest new data, but also new reprocessing of old data. We also have to just continue to maintain and serve this vital repository of irreplaceable data. That means that we have to make sure that disks still work, that hackers stay out, that operating systems get updated, all of that infrastructure stuff. We have to support observation planning, but also in the context of NASA, mission planning. There's tons of original science that is waiting to happen in the archives, and we have to serve high-level science products, meaning data that are ready to use right now you can get from the archive. And we have to enable cutting-edge research at all levels. APIs are application programming interfaces, which means that you can build software that interacts directly with the archive. Virtual observatory are protocols that allow one kind of interface that talks to observatories all over the world. We have to be able to provide user support by experts using that data. We have to be able to provide new and enhanced services all the time, and we have to easily enable multi-wavelength projects. And ease of access is really important because we have to support professional astronomers at all levels, by which I mean the people who built the instrument and really want the raw data. We also have to support people who've never used data from that instrument before. We have to support an emeritus astronomer who can barely read his email, all the way through a summer student getting started on her first research project ever, and everybody in between. All of those people need to be able to get and use data. And that means that you can too. And that also means that resource-limited astronomers in this country and everywhere around the world can access data too. So that means we have to have an intuitive web-based interface, which means there's no extra software that needs to be installed. There has to be visualization of the resources that we have available, the data, lots of tools that are available, and easily found choices to look, just give me the data, just give me the table, just download the data, easily available. And there needs to be easy to access help. There needs to be a promptly answered help desk, all of which we provide. And having those ready to use data products means that the barrier to using the data is lower than it has been really ever. We need to have all of that knowledgeable staff who've done science with the data products, who can help find problems and pass on the valuable experience to new users. Our help desk has to be really fast and really accurate because the questions that we get can be really, really complex. We need to have really good documentation. We need to have really regularly updated tools and updated data releases. We need to update our documentation frequently in response to the questions that we're getting. We have to provide live demos and recorded demos like this one. We have actually those numbers are out of date. We have more than 100 videos and thousands of views of the URSA on the URSA YouTube feed. And the complexity of the needs that the user community has just increases with time. And it turns out that having a really good archive doubles the scientific output. On this plot, there's unfortunately two different color schemes and two different units, but this is the percentage of journal articles as a function of time for Spitzer. This is Spitzer archival research. This is a Spitzer PI research. In other words, the people who requested the observations are writing the paper. And these are people who didn't request those data writing the paper. And then that red wedge is using both PI data and archival data. And you see that half of the papers are archival data. This is Hubble data. It's a little bit different units. This is total number of papers, not percentage. Also as a function of time. Blue is non-archival, but here red is archival and green is both. So again, half of the papers are archival research. So having a good archive doubles the scientific output that your observatory produces. So some of the NASA astrophysics archives that are available. So IPAC has many. URSA is the Infrared Science Archive. It specializes in NASA's infrared and submillimeter data. NED is the NASA Extragalactic Database. There's the NASA Exoplanet Archive, the Keck Observatory Archive. Space Telescope Science Institute has MASS, the Mikulski Archive for Space Telescopes, which has UV, optical, and some infrared data. The Goddard Space Flight Center has HIASARC, which is high energy and cosmic microwave background radiation. The Smithsonian Astrophysical Observatory and the Center for Astrophysics at Harvard has ADS, which is the Astrophysical Data System, which is all of the astronomical literature from the 1800s through this morning. It's all available there. And it also has the Chandra X-ray archive there. So lots and lots of archives. It turns out at IPAC, we also have something called AstroPix, which is really useful. It also, that pulls together all sorts of like press release images. So that's also really, really useful. So just for context, Caltech is the California Institute of Technology. IPAC is at Caltech, but it's not part of the astronomy department. It's a totally separate entity. IPAC has 35 years of experience with archives and science operations. We run both archives and flying missions. We hire both astronomers and programmers. We have a visiting grad student 6 months fellowship, and we do all sorts of interesting things with that. But just for context, let me just show you some of the archives at IPAC. NED is the NASA IPAC Extragalactic Database. It is, of course, focused on extragalactic science. They ingest catalogs and literature tables. It's a curated collection of data. So they have hundreds of millions of unique objects. They have myriad crosslinks and notes. They release updates every few months. That's their URL, and that's what their webpage looks like. The NASA Exoplanet Archive, unsurprisingly, focuses on exoplanets and their host stars. They have Kepler and K2 data as well as Corot data. They have lots of online tools to work with these data, like the Periodogram service. That's their URL, and that's what their website looks like. I work for URSA. URSA is the NASA IPAC Infrared Science Archive. Our charter is to provide an interface to all of NASA's infrared and submillimeter datasets. We have a few other datasets in there as well. Some of our datasets are very, very small, and some are very, very large, like all sky surveys. URSA datasets are cited in about 18% of all astronomical refereed journal articles annually, and we have just petabytes of data. Several of the very newest datasets are served via a software package called Firefly. The rest are accessible via other software packages at URSA. And we have literally petabytes upon petabytes of data, billions of rows in catalogs. And this is what the URSA website looks like. Just some of the URSA holdings include IRAS, which is the first all-sky mid and far infrared survey, 2MASS, which is a ground-based all-sky near-infrared survey, the Spitzer Space Telescope, which is a pointed observatory between 3.5 and 160 microns, WISE, which is the Wide Field Infrared Survey Explorer, which is an all-sky survey between 3 and 22 microns, the Herschel Space Observatory, which is a pointed observatory between 60 and 670 microns, Planck, which was a European all-sky survey, the Cosmos, which is a multi-wavelength pointed extragalactic survey with a particular 2 square degree field, Bolocam, which is a millimeter wavelength ground-based observatory, Akari, which is a Japanese infrared telescope, which is an all-sky survey, MSX, which was a Air Force survey that mapped the galactic plane, the ISO, which was a European mission, and ZTF, which is a ground-based optical monitoring of the sky visible from Palomar. This is some of URSA's tools. This one is called Finder Chart. It's kind of the easiest on-ramp to URSA services. It gives you access to 7 different surveys at once, and you can search images and catalogs together. You put in your target, and these are kind of the results that you get back. Images sorted by survey and catalogs and plots at the bottom. This is the generic URSA viewer tool. Does it look kind of familiar? Indeed. Here are some of the images that you get back sorted by wavelength. Here's the ZTF image viewer. You getting the idea that it kind of looks familiar? The idea is that it all kind of looks familiar. So once you master one, they all kind of look similar. Here we've got a list of images on the left and the image results on the right. So yeah, basically many of them have the same look and feel. We're updating tools and data all the time. Not everything is served this way, but we're getting there. And then URSA can also seamlessly interface with many other archives, some more easily than others, and this tool will improve with time. So there's lots and lots of data available right now. Almost everything is web-based. Most are pretty intuitive, at least I hope so. Most have online help, and things are getting more and more integrated all the time. And of course, the URSA YouTube channel has tons of videos.